Today we have a great pleasure and honor to host Professor Robert Iskander from Wrocław University of Technology. Professor Iskander made his PhD in Australia, in Queensland University of Technology in Brisbane, in Australia. And then he spent several years in a few scientific institutions in Australia. And from around 10 years, he's in Poland, in Wrocław. And he specializes in physics of functions of the human eye, of eyesight, of analysis of biomedical signals and images. He's not only a researcher, but also an educator, a tutor. Maybe it is enough to mention that he was a tutor for 17 past PhD students, and currently he's a tutor for 7 PhD students at the same time now. Yes, he's also an author of patents in the domain of devices, optometric devices, above 10 patents, and an author of more than 100 scientific publications, cited over 3,000 times. So maybe I will now pass the microphone to Professor Iskander. Floor is yours.
Sure. Thank you very much. Can everyone hear me? Yes, I can see some nods there at the back. It's an enormous pleasure to be here. This is my second time when I'm in this particular building, not in this beautiful room. My CV has been sort of already went through. But I'm going just to tell you a little bit about my journey. And my scientific journey was that my background is in statistical signal processing. So I'm an engineer. So you here mostly, you are physicists, right? So I look at things from a very pragmatic point of view. And as you could see, my title of my thesis when I was doing my PhD was related to something which we called over-the-horizon radar, and it's essentially a radar that looks beyond the horizon, right? So you're using a high-frequency range of electromagnetic waves that bounce from the ionosphere, and you can look beyond the horizon. And essentially, what I was supposed to do when I was finishing my PhD, I was supposed to be in this place called Adelaide, and let me just see whether I can get yeah. No, this is not what I was looking for. Okay, so I use my mouse. So another light is somewhere here, and I studied here in Brisbane. Essentially, I got a job with the Australian Defence. It's called DSTO, Defence Science and Technology Organization, and I had to wait on this side. Yeah? No? Yes, thank you very much. And essentially, I had to wait for something which is called security clearance. And normally, when you finish your PhD, you're looking for a job. And then I found a very interesting job in the School of Optometry and Vision Sciences of the same university. And I was here in this set of blocks, actually in this particular, it's an O wing of this building. And the beauty about it is, as you could see, the majority of the picture here is the golf course, right? So this is the place where you essentially have all your technical meetings, and you'll be surprised how much great ideas were coming between the discussion whether I should use a 9 club or a wedge to hit a ball. So that was basically what I was doing for many years, and I enjoyed that time immensely. But in 2010, I moved back, as I call it, to southwestern Europe, because as you could see, We are in Wrocław, you as well in Warsaw, you know, a little bit away from the geographical center of Europe, which is in Suchowola. So we are in southwestern Europe. And when I moved, I had to do my habilitation, and it was about modeling and estimation of optical characteristics of the human eye. And I'm saying I had to, because in Australia, obviously, you don't need to have this kind of a degree. But when I came here, I wanted to continue my work also as an educator, as it was mentioned. So I needed that in order to have PhD students. When you look at my works and areas that I tackled in my life, when it comes to eye, of course, you can see that I've been going through. Okay, this is not good enough. So no, it's there, but I think I'll use the mouse. So there are 3 parts here. So I spent quite a lot of time on anterior eye, and I spent a lot of time on visual optics, and I spent a lot of time on ocular pulse, and now I'm spending a lot of time on diagnosing glaucoma. And it seems that all those paths which I were having in my life are essentially pointing me into that one particular direction. Obviously today, because we are dealing with physics, I decided just to talk about visual optics. When we look at the human eye, this is what students may learn. This is, I call it, web-based popular view. And you can see that an eye is essentially compared to a camera. Some of the young students, they may ask what is film, because now they wouldn't know what it is, unless they had some photography lessons. But for me as an engineer, I actually view the human eye in a little bit more complex manner. And as you can see here, I see this eye as a dynamic system. And this dynamic system looks like that the whole eye is moving. Right? We've got eye movements, even if we look at just one particular eye. And then when you look at an input image, that image has to go through the tear film, and the tear film is just few microns thick. And then obviously some people classically divide this thin film into layers like mucin layer, water layer, lipid layer. And then if you go inside, then you realize that in the water layer you've got a few thousand proteins. When you look inside the lipids, there are hundreds of different lipids there. And this is not just a monolayer, so you can go deeper and deeper and deeper. And the whole thing is changing all the time. You blink, and there is a whole process of forming this tear film. You want it to be optically perfect, right? Because this is your first refractive surface. And there is a dynamics already there. Then we have the cornea, and the cornea is also changing. Also, the word cornea is derived from horn, right? And in Polish you say rogówka, right? So when you say rogówka, you're thinking that this has to be something which is hard. No, it's not hard, it's quite soft, and it's enough to sort of do something like that, and you'll be introducing about 3 or 4 diopters of astigmatism just by pulling a little bit your eyelids. So the cornea is also changing. Then you have a pupil, which reacts to the amount of light that is coming into our eye. So it is dynamic, and it's not only that it is going smaller or larger, it's also vibrating. You've got something which is called hippus. Then we've got crystalline lens. This is actually an ingenious device, because this device allows us to accommodate, right? It allows young people to accommodate. People like myself, it allows to accommodate less. And maybe for some of you, you are left with very, very little accommodation. And well, that's the aging process, and we can't do much here, although there is quite a lot of area that engineers and physicists and people that deal with optics, they try to devise something which we called accommodative IOL, intraocular lens, that would have the possibility to sort of mimics accommodation. This crystalline lens on the pupil, and also the retina, which someone may say, well, it's a static thing at the back, like this film in the camera. No, it's not true. We've got something which is called the cardiopulmonary system. So this is basically your lungs and your heart, and we are breathing, and our heart is, beating all the time. And all this is actually causing the eye to form an image at the end. And as you can see that image at the end, I did a little bit of simulation there just to defocus it a little bit. Because in a true eye, even if you are an ametrope, so a person who doesn't need to wear glasses, right, that image is not perfect, and it's not going to be perfect. Okay, so let's have a look at what we just said. We said that the eye, we cannot view it as a camera, right? We have to view it as a dynamic system. There is a lot of things changing in this eye, but as you can see, my glasses, they are not dynamic, right? Your glasses are not dynamic too. You don't have an adaptive optic system built around your eyes, like, you know, goggles, which would look like this, right? So we cannot really compensate all the aberrations. Our compensation is static, and we have to learn quite a bit about this dynamics in order to come up with really, really good static correction. And in order to do that, what basically we do, we measure something which we call wavefront aberrations. How we can measure these wavefront aberrations? Well, this is just a schematic, very basic configuration of a system in which you can actually measure aberrations. So you've got this laser beam, it's collimated, and the red line essentially goes through those mirrors into the eye. So we are basically putting a very narrow beam of light into the eye. Why it's very narrow? Because if we put it a beam which was wide, it would go through the optics, and it would carry also information about the deformations that are happening on the cornea and the crystalline lens. So basically, with that beam of light, what you'd like to do, you just like to illuminate the retina, okay? Make the retina flash, like you make a picture of a cat, you know, at night, and you see how nicely their eyes are flash, okay? So we've got something which we call Badal system. This Badal system is essentially the stage where we can change the defocus, because defocus is quite large in the eye, and for some people like myself, it can be over 6 diopters. That's quite a lot. For other eyes, it might be hyperopic, so it might be on a negative side in terms of the aberration. And the light which is coming through is going through the same system. The person is viewing the target, and we have something which we call wavefront sensor. And when it comes to wavefront sensor, I'm going to use 2 slides here, which are slides of my colleague Ray Applegate, who works in Houston, quite famous optometrist, and they produce those nice slides, and everyone is using them. So basically, this is the principle of something which we call Hartmann-Schack sensor, or some people refer to it as Schack-Hartmann sensor. Well, I call it Hartmann-Schack because Hartmann was first, and then Schack was the second one. So when you have a perfect waveform, which is just a plane wave, it goes through something which we call lenslet array. So this is just an array of small lenses. And then on your video sensor, what you basically see, you see a set of point-spread functions, right? And those point-spread functions are regular according to the grid formed by those lenslet arrays. But if you take an aberrated waveform that carries some information about your system, then obviously those dots are not perfectly aligned. And then by calculating the transversal aberrations, so your delta x and delta y, you can basically calculate your wavefront by noting that those transversal aberrations will be proportional to the slope of your wavefront error. We can also do something like this, that we do not need to go through the whole system. We can learn quite a bit about the eye simply from the cornea. And someone will say, why the cornea? Why we do not look for total aberrations by just corneal aberrations? Well, for corneal aberrations, what we do, we have to do ray tracing, and we can do this ray tracing either in 3D and then fit certain functions. Right? So we will have the corneal wavefront. Those functions traditionally would be Zernike polynomials. Or we can do this in 2D when we'll be looking at refraction angles, and then go to the domain which we call refractive power domain, and fit other functions to the refractive power domain to get some Zernike coefficients. And in this case, we are losing 3 of them. We are losing the piston, and we are using the prisms. But the piston is not an aberration, so we don't care. And the pistons and the prism, sorry, they are not aberrations either if we consider just monocular aberrations, right? They are important when we have to fuse images from two eyes. There is not much difference for majority of eyes. And why that information would be useful? It is useful because the crystalline lens is quite similar when we look at the population, but corneas are not. Corneas are different. Corneas carry a majority of the astigmatism. And if you consider, for example, nowadays a refractive surgery, some people may say, we will do a custom surgery for you, but this custom surgery can be topo only, which means that we will take only information about your topography of the cornea and then based on that information create for you a custom-made surgery. When it comes to the wavefront modeling, what we basically will say is three things here are important. First of all, that this wavefront variation in the wavefront in space we will basically describe by something which is called wavefront error function, and that wavefront error is essentially your wavefront taking away the sphere, the best fit sphere to the wavefront. Then what we will say that if we look at the dynamics, we will be considered time-varying wavefront error function, and it's good to use some polynomial series to basically describe certain aberrations. And let's consider first the static case. This is how we build the Zernike polynomials, okay? Fritz Zernike, a famous physicist, he was a Nobel Prize winner, right? He constructed the phase microscopy. Basically looked at, okay, we've got a two-dimensional function, wxy. We can do Taylor series, so just expand it into some coefficients. Then we perform the Gram-Schmidt orthogonalization on those, and then we'll use also some invariance constraint when it comes to the rotation. And they came up with, him and also his student, he came up with those polynomials. As we can see, they have this radial term, which is either on its own, this is when m is equal to 0, or it is also modulated either by the sine or cosine function to form either even or odd terms of those polynomials. And the nice thing about these polynomials is that they are very, very easily to implement. We basically used linear least squares. Here you've got the equation for A, right? The well-known, where you've got the Penrose-Moore pseudo-inverse times W, which is the wavefront. So this is essentially the basics, but I wanted to tell you about this because the problem that you may have in situations like that is to ask yourself how many terms we actually need to use in order to describe a particular wavefront aberration, because you may say, okay, I'm interested only in so-called lower order aberrations, right? So then I would use 6 of these polynomials. Then you can say, no, I'm interested in high order aberrations as well. And when you look at high order aberration, then the question is, it is the 4th, the 6th, the 8th, how many of those Zernike polynomials we would need to fit? Particularly when you look at your data set from a wavefront sensor where you may have about 1,000 data points to play with. So essentially, you would be looking at a large number of coefficients if you want to do this. This is the point where I actually would like to give you a little bit of a digression, okay? This will be a small digression. What I'm basically trying to do here is to convince you that it is not always to use a lot of these coefficients. What I've done in here, I essentially considered now a very simple linear model, and I added to it some noise. As you can see, the noise is normally distributed, it has got 0 mean and variance equal to 1. And if I will now calculate what would happen if calculate the root mean square error, that's that single point over there, when I fit a line here. So I can fit a line to this data, but I can fit a second order, a third, and so on, and I can basically go until at some point someone will tell me, in this case this is MATLAB telling you, hey, stop, this is too much, your polynomial now is badly conditioned, there is no point of fitting 12 or 13 polynomials. But the mean square error or the root mean square error is getting smaller and smaller and smaller. So basically in situations like that, what we try to do, we try to use some penalty function. We add that penalty function to our mean square error, and in this way we're getting an information criterion. One of them you probably know, it's called Akaike information criterion. And there is another one which is called the minimum description length, the MDL of Reasonen from 1976. So this is basically the approach that can be taken. Someone may say, okay, these Zernike polynomials are the best that we can come up with. And the answer is, of course, no, because we've got so many possibilities. You've got actually an infinite number of possibilities to fit a two-dimensional data, okay? And one of them was proposed by Bhatia and Wolf. Some people refer to as pseudo-Zernike polynomials. And as you can see, the only difference here is actually that in the Zernike polynomials, we were applying this Gram-Schmidt orthogonalization to monomials xi, yi, and in this case, we would like also the r, so radially, we also would like them to be orthogonal. And essentially, they look almost the same. They are described now not with r, but with t, and obviously, we would have to recall what the Zernike polynomials are. They look similar. They look similar, but they form completely different set of basis functions. And here you can see that for the first radial order, we not only have the prisms, but suddenly we have a cone in the middle, okay? And rather than having an astigmatism, which is for the second order, we don't have a defocus anymore, but we have something which I would call comma-like, and in the middle, the Mexican hat. And then you would sort of think, where is the Mexican hat coming from? Okay, these are the slides which I had at once. There is this conference we go every year, which is called ARVO. This is Association for Research in Vision and Ophthalmology in the United States. And I had this talk, and one night before, we had few drinks. So when we had few drinks, we had to decide how we would call those aberrations which nobody has called them before. Are we going to simply call them B20? The Mexican hat was a nice thing, and you can see that we were even better here because we had a bird feeder, we had a snapdragon, right? The trefoils are also in the Zernike polynomials. And for the fourth order, we can see that even we've got the bubble wrap, so, and a water drop. And what is the snapdragon? The snapdragon is a kind of flower which, for those of you who do crosswords, they will know there is a word called vizhlin. I don't know whether you're familiar with vizhlin, but some of you might be familiar with something which is called the lvia pascha, right? And this is just a kind of vizhlin. And this is our snapdragon. So you can see that you can play with it. And then people may say, okay, is it worth playing, okay? Well, let's try doing this, okay? You can basically say, if I use the fourth order Zernike polynomials, okay? Then what I will have 15 terms. And if I use the fourth order Bhatia-Wolf polynomials, what would I have? I would have 25 terms. But that wouldn't be fair comparing 15 terms to 25 terms. 25 terms will always perform a better fit as I was showing you. The more we fit, the mean square error gets smaller and smaller. So we don't want that. We will say, okay, we'll just cut the first 15. What will happen? And when we do that, we can see that actually we are getting, in some cases, this is actually a keratoconic eye, and we are comparing the fit of the Zernike polynomials to the ones of Bhatia and Wolf. We have the same number of terms, but the fit is actually better. So you can do better than the Zernike polynomials if you really want. Now, when you look at all the methods that people came up with, you'll see that, well, we start with Seidel. This is something for people who deal with optics, obvious. And you will see that there were papers by Tyson, Conforti, that they were changing from Seidel to Taylor, from Taylor to Seidel, and so on. Zernike polynomials in 2004 became standard for characterizing wavefront aberrations of the eye. And then you've got a lot of other things. I came to play there as well in 2007 with the Zernike refractive power polynomials, which I will recall them in a moment. But there is a lot of good things which happened because those Zernike polynomials allowed those optometrists and ophthalmologists who now talk about, oh, you have got this subject or a patient and he had 0.6 microns of coma, right? They forget to tell you also what was the pupil size, right? but they are quite excited because they know what those Zernike polynomials are, but they still cannot really relate to what it is in diopters for them, because majority of optometrists and ophthalmologists, they actually learn about, when they measure the eye, their principal unit, we would say, is diopter. So let's try to sort of say, can we relate those monochromatic aberrations to something which we can now understand in terms of the refractive power in diopters? And we can. And some people like Larry Tibus already, that was a long time ago, 20 years, more than 20 years ago, he was basically saying, okay, we've got this orthogonal components, okay? So those of you who wear glasses, you are probably aware that you've got some, you've got corrected defocus with a sphere, you've got some astigmatism corrected with a cylinder, and that cylinder has to be at certain axes. So we've got three parameters, S, C, and alpha. And those parameters, if we did some stats and tried to add numbers together to calculate, for example, the mean or the variance, that wouldn't work. So we have to change them, those sphere, cylinder, and axis, we have to change them in such a way that they are orthogonal to each other. And to do that, we have those three vectors, mj0 and j45. What basically Larry was saying is that, okay, we can relate those mj0 and j45. We can estimate them, knowing the pupil radius and knowing what the wavefront aberrations are coming with these coefficients C20, which is the fourth Zernike polynomial. This is just a defocus term, C22 and C2 minus 2. This means that this is again second order, but with the azimuthal frequency of 2, describing the astigmatism. And if your wavefront was only measured using these three coefficients, that would be okay. But if you have more coefficients, then you are realizing that your sphere, or the mean sphere, or the mean equivalent, people call it, this m hat, is actually the C20 and C40 and 660, 680, and so on. So we don't really know how many terms again to take. But then my question would be, but maybe there is a way, because I'm an electrical engineer, right? So for me, Fourier is the basic thing, right? I go from one domain to another domain. So I was thinking, can I go from one domain to another domain? Here is domain which I call W, and here is another domain which I call F, which is the refractive power domain. And indeed, you can do that. And again, they look familiar. They look very similar to what the Zernike polynomials are, but these are not Zernike polynomials. I call them Zernike refractive power polynomials. So they look a little bit different, okay? They look a little bit different, but then you have this so-called pyramid, but this pyramid is now, like when you see the pyramid of Zernike polynomials, this is the pyramid like in Giza, right? And this is more like the Mexican pyramid because we are losing the terms, right? We cannot have the terms related to the prism. And now the defocus, the middle term, is constant, right? Because defocus is constant across the whole eye. But then when you're looking at the chromatic terms, which are the first two middle in the second row for n equal 3, then we can say that I have that much comma, let's say vertical comma, per millimeter. Let's say I have 0.5 diopters of comma per millimeter. So then people may see, oh, that's what happens across this pupil. Because if you say, I have a pupil size of 5 millimeters and I have 0.6 microns of comma, vertical comma, let's say, people don't understand that. But when you tell them that this is now in diopters per millimeters, then they can see some progression happening from the bottom to the top of your pupil size. And when we did that, we also realized that if we look at those representations and compare that to subjective, then we sort of slightly outperform the other two methods which Larry Tibus proposed. So we were good on that. And then there were pros and there were cons. What were the cons? The cons were that those Zernike polynomials which I have created in refractive power domain, they were not orthonormal, or they were not orthogonal, and they did not they were not forming a complete set of basis functions. And basically at that point, I teamed up with Larry and Jae Young Nam, and that was a PhD student from Korea that was doing her PhD in Bloomington in the United States. And we basically sat together and decided to do something nice about it, and we managed. And that's in a moment, but just to show you some clinical examples here, how a wavefront would look like and how the divergence map or the refractive power domain for those wavefronts would look like. And those images which are on your right-hand side, these are the images that optometrists and ophthalmologists are familiar with when they are looking at the power maps of cornea. But here you've got for your total wavefront. And here is like if you need some more information, as we can see, we started in 2007, then in 2009 we had 2 papers, one in JOSA about this, and then we essentially tried the same information to describe that in clinical and experimental optometry, so optometrists can actually learn something about that, and for that we got the Best Paper Award for in 2010 for the years 2007, 2009. Okay, that's the static case. Now let's have a look at the dynamic case. Now this is quite interesting because, as we said, the whole thing is not static, and what we would like to do now is to look at certain elements here which makes that eye a little bit dynamic. How we can do this? Well, we've got those wavefront sensors, and this particular one that I worked with was called COAS. In Europe sometimes that was called WASCA. Zeiss bought it, then AMO bought it, and now nobody can use it. So basically that's the short story of a very nice development in Albuquerque in the United States, in that basically there was this company, small company, that developed those wavefront sensors. They were very, very popular at the beginning of the millennium, but now you can only hope to buy one on eBay. So basically what happens is that in real time you can collect those Hartmann-Shack images, and when you're done with your measurement offline, you can basically do the wavefront estimation, and then you can do the polynomial fitting of the wavefronts, and then you can see what's happening. Now this is an example of a person looking far, okay? And we're looking at one particular term, which in this case is Z20, or in previous slides that was called C20. So it's your defocus, okay, or the component which carries most of the information about defocus, because when you're looking at the Z40, there is a little bit of defocus there as well, and also high order aberrations. All those which are secular symmetric, they carry some information about the defocus. So let's say that we will call that a defocus Zernike term. It's not a pure defocus, but it's a defocus Zernike term. And basically we do all those measurements, and we can see that they are not necessarily the same. And then when we look at closer target, then our eye accommodates, and then they look a little bit more the same. And then if you do the Fourier transformation of this data, you will realize that you're getting peaks there, and those peaks will be related quite closely to your pulse and to your respiration. So we can see that these dynamics that we see are related to your cardiopulmonary system. Now let's have a look at this myope here. This is an accommodated myope, so nobody's accommodating here. We've got 4 measurements, and here is just a simulation of the letter that this person would be viewing. And we've got 2 estimates of our refractive power. And someone may say, okay, you've got 3 measurements which are quite close, 1 measurement which is not close. Are those differences really significant from the clinical point of view? And we can see that the difference in sphere is 0.36 diopters. And if you look at the best sphere, so basically taking into account the astigmatism, we're having 0.3 diopters as well. Around that, right? Around that. So it is clinically significant, because everything that is larger than quarter of a diopter would be clinically significant. So let's go back here and basically look at this Z20 term, okay? most likely people would say, if they were doing their master's degree, I don't like this measurement, I'm going to leave it, I'm going just to perform the analysis of the other 3 measurements because this one looks like an outlier. But for the same measurement now, let's have a look at the 4th order term. And for the 4th order term, well, that 3rd measurement looks like an outlier. Well, let's dig a little bit more and let's have a look of what's happening to the chromatic terms. They're all over the place. Which one should I reject? There is nothing to reject. This is the dynamics of the eye, and we have to essentially take it as a whole image, right? We cannot just analyze a single Zernike polynomial term on its own. Does not make sense. So when you're taking those measurements of the dynamic wavefront, right, they are your estimates of your true refractive state of the eye. But do not discount a particular term. It has to be taken as a whole. Here is an example of the simulation of this first measurement, then the second measurement, then the third measurement, and the fourth measurement. This is still the same eye. This is the same eye. So as you could see, we realized that the dynamics of the eye, because someone might say, for which of these measurements should I do the correction? Right? If I was performing there, because we will move to that in a moment, but if you had an adaptive optics system, you would say, I can correct those aberrations, right? But which ones would you correct if you now looked at a static correction, not a dynamic correction? So basically, what we decided to do, we decided to re-examine the role of cardiopulmonary signals in the dynamics of wavefront aberrations and provide some conclusive evidence what is actually happening, because as you could see here, there were people who were saying that they are sort of weakly correlated. This is Karen Hampson in 2005. She published a very interesting paper saying that, well, essentially we shouldn't really worry about that because the connection is poor. So what we did, we decided actually to test that. And when we decided to test that, we took a person, we measured the aberration. On the top plot there, you've got one of these, right? That's the focus Zernike term. But at the same time, we look at the respiration, we look at the pulse, and we also looked at the ECG. Obviously, you have a lot of things here. We're not going to go through this in detail, but there were 9 young subjects. We used the metronome in order to stabilize their breathing, but we also looked at when they breathe naturally, what happens. And we took some measurements of those wavefronts, and we had to do some signal processing of this data. First of all, what we did, we had to take into account the measurement noise, jitter analysis, different stability, and so on, so on, so on. But this is just a topic of completely different seminar. Here I would basically say that we did not consider those signals to be stationary. We considered them to be non-stationary, but to be also sure what we decided to do, we decided to test this stationary. Okay? So just for you, a quick reminder of what I mean by stationary processes. Well, the mean, so the expected value of your process has to be constant, your variance has to be bounded, and your autocorrelation function has to be just a function of your lag, rather than just being a two-dimensional function of time and the lag. And we use here a test which we done in a stationary test in a frequency domain, which essentially look like this. Again, this is just telling you that what we realize is that if you take the logarithm of your arithmetic mean and you divide it by the ratio of the arithmetic mean and geometric mean, then this is equal to 0 only if A1 is equal to A2 and so on. And we did that essentially for chunks of data in the power spectral domain, and that test essentially showed that majority of our data, except for the pulse, okay, except for the respiration. The respiration sometimes seems to be, particularly when we were breathing on the metronome, that signal was not rejected by that test. But majority of signals like ECG or pulse is being rejected, and it is indeed a non-stationary signal. Now, a few examples here just to tell you, because I'm going to show you a few pictures here in time-frequency domain. So basically, they're going to look like this. In the middle, we have this time-frequency representation. On the left-hand side, we have a power spectrum. On the top, we've got the time domain. And when you've got the sinusoid, you've got a single peak, and that peak sort of is in time. It's not changing, but when you now deal with signal which is non-stationary, like for example here, we can say that this is re, mi, re, do, right? So if we played this kind of music in power spectral domain, we wouldn't know what this, it would be, let's say, mi, re, re, do, and still you would end up with the same thing. But time frequency representation essentially showing us the right music. And when we got the chirp signal here, just a linear FM signal, then in frequency domain, it looks like this is just a broadband noise, but this is not a broadband noise, this is a particular frequency just changing in time. And what we got, we actually used here something which we call ZAM distribution, Tau Atlas Marx distribution, one of the time frequency representation belonging to the Cohen's class of distribution. And we've got A is your pulse, B is your respiration, C is your ECG, the heart activity, and D is your defocus. And this is quite interesting because in defocus we can see clearly that something is basically happening also in a non-stationary fashion, because you can see that the frequency that it is related to your respiration is sort of present in your defocus, but the frequency which is related to your pulse and ECG is for some period of time, and then it disappears. It's no longer there. And when we did some analysis there, then what we basically had to do, we had to find some measures of this relationship between the signals. And for that, we use the time frequency coherence. The time frequency coherence is sort of like an extension of frequency domain coherence. But for it to be really, really good, it needs some requirements. And these requirements set by White and Boischache in 1990 and Matz and Hawash in 2000. And what it basically requires, it requires you to have a window. So you have to do a little bit of windowing there. And we use a particular window that looks like that. It's a Gaussian window essentially, right? But it's got different sigma for time and different for frequency. We look at the frequency support, we look at the time support in order to get these things right. And then this is what we got. This is pulse versus respiration. Okay, so please focus on the other monitor. This one doesn't look good. Hopefully this will be switched off, or not to confuse us a bit. And you can see that this, when we look at the pulse and respiration versus ECG signal, then this coherence is very, very high between pulse and respiration, and also between pulse and ECG. The same thing here, defocus versus pulse, respiration and ECG, and we can basically see that this coherence is in some places high, in some places it's not high. And for that, what we basically needed to do, we needed to put some masks, and we decided to have masks which would be related to your pulse and respiration at 3 dB level, and then average all the information there. And when we look at this average coherence, we had to basically say Karen Hampson was right, because none of these coherences were very high. As you can see, the highest that we got is 0.5. Again, coherence is a number that it is between 0 and 1. So 0.55 is sort of medium type of relationship between these two signals. But then when you look at normalized time of high coherence, so we decided, okay, let's have a look how much time the eye is in a state where the coherence between the aberrations, in this particular it's defocus, for example, and your respiration, it looks like for 40% of time that we measured, this coherence was high. 60% was low, right? On average, it was 0.55, but at 40% of time, it's higher than 0.075. So basically what happens? It happens the following. We can see that the defocus in particular would be related to changes, let's say, in accommodation. Okay, so the heart is pumping and this is the crystalline lens is changing its shape. And you're getting your defocus modulated in this way. Fine. We should have a perfect coherence in this case, but we don't. We have sometimes and sometimes we don't. What does it mean? It means that we have another element in our system, and that element is your fundus, is your retina. Because now what you have a retina that is pulsating, and you've got your crystalline lens that is pulsating. And when the two happens to be in phase, then suddenly your coherence is high between your defocus and your pulse or your ECG. But when they are out of phase, they are not. So basically, with this work, what we actually proved, we proved that in the eye, the dynamics of people call it microfluctuations of your wavefront aberrations, their only source is not only coming from the crystalline lens, but also from the fundus pulsation. So this is essentially the partial conclusion that you have in here. And we have to move a little bit quicker now, I can see, because I've been told that I have up to 60 minutes. So, okay. Estimation of the depth of focus from wavefront measurements. This is an important issue. Basically, how we do those sort of things. We first use some image quality matrix, and in our case, this image quality matrix, sometimes it's called visual Strel ratio. So you are probably familiar with the Strel ratio. I mean, those of you who deal with optics obviously are. Visual means that we add to it also a certain visual component, which is we can call it a visual component. We sometimes can model it, sometimes we can measure it. It's called contrast sensitivity function. When you do something like this, that you're looking then at your visual Strel ratio, and this visual Strel ratio on this graph, it is a visual Strel ratio which is based on optical transfer function, because you can calculate also this visual Strel ratio in the point spread function domain. And you can see that, okay, what basically happens is you have so-called through focus curve. At some point, you have the highest quality of your image, and then if you are moving from your focal point, then it drops. And there are three papers which dealt with this, trying to set up what would be a good threshold to derive this depth of focus. And Susanna Marcos tried in 1999 setting up this threshold at 80%. Some people like Legge and Jansonius, they set it up at 50%. But it might be somewhere in between. Well, it might be not necessarily too high or too low, because what you would like to do, you would like to set it up in such a way that this threshold should be equivalent to your subjective depth of focus that you have. And this curve is actually very important for us now to think about correcting vision. Suppose that we would like to correct all the higher order aberrations in the system. What would happen with that curve? Well, first of all, it would shoot to 1. At 0 defocus, it will be equal to 1, and it will be going down quite quickly from that 1. Your depth of focus will be very, very small. So essentially, having those higher order aberrations in the eye, let us have a decent depth of focus. If we correct all the higher order aberrations, we won't have that. So how we can now calculate this through focus curve? Okay, to calculate this through focus curve, we load the wavefront error, we set the pupil size, and then we do this transformation which I was telling you, that we're going from the domain of W to the domain of F, from the wavefront to the refractive power. And this is important because when we do that, then we are in diopters, not Zernike polynomials, but in diopters. And when we have that, we can remove this cylinder, because you can remove the sphere easily by subtracting the mean value, and you can subtract your cylinder by doing a least square fit with the cosines and sines. And then when you have this now pure higher order wavefront without any defocus, then I can start adding defocus and essentially using software deriving it for this image quality matrix for different values. Here the VSOTF, as you can see, there is an equation for it, and you can see that it's essentially the optical transfer function. We take the real part of it. There is a reason for that, why we take the real part, and then we multiply it by the contrast sensitivity function, and we take a ratio between this optical transfer function and the one that is without any aberrations, that is diffraction limited. What we basically realized is that if we now try to take people, measure their subjective depth of focus, at the same time measure their aberrations, and now try to compare these two things together, so what we basically ended up with different thresholds, right? For every person, we ended up with different thresholds. And you can see that for some people, the threshold was around 50%, for some people was around 80 few percent. And then you can do the regression, and what you have on your left-hand side is for 5 millimeter pupil, and what you have on the right-hand side is for 3.5 millimeter pupil. So if your pupil is large enough, you can actually come up with a threshold level that is predicted by equation like this. And that has been published with one of my PhD students who graduated a long time ago, Fan Yi, in Journal of Vision. So for you who are interested in that particular area, then you can see that from a single wavefront, you can estimate now the whole through focus function. Okay, I need to be really, really quick. Supervision. Okay, so very quick topic here. This is a few slides about the dream that did not come true. Well, essentially everything started in the 90s. I try to keep, because I know that for some of you, you are now closing your eyes. It's becoming quite a long thing, so just for you to have a little bit of a break. But what basically happens? Here we have two people. One of them is essentially Jerry Nelson, director of the National Science Foundation Center for Adaptive Optics at the University of California, and also Rob Williams, David Rob Williams, who's the co-director of Rochester Center for Vision Science. And basically what they were saying, this is June 2000, and that's what Williams said. We haven't quite created a perfect eye, but we've created the best anyone ever seen. Then I was just in the lab looking at the boring old letter E on the screen, but even then I was so excited by how much crisper and clearer the image appeared. That was Nelson. And essentially they were bragging about the supervision difference is particularly noticeable in low light when most humans can't see very well. Subjects reported a twofold increase in contrast sensitivity using supervision in this situation. So there was a lot of hype. And you may sort of think, well, am I different? No, I jumped on a wagon together with them. I was so excited about the idea that I spent a lot of years trying to develop in a team with Johnson & Johnson contact lenses that would actually correct those higher order aberrations. There was a lot of hype. But unfortunately, we are now, 20 years later, and we are proverbially back to square one. It didn't happen. I mean, obviously, we have something which we call the custom surgery. You can correct your higher order aberrations. The question is when. And the answer is when you have pathological amounts of higher order aberrations. But if you have naturally present higher order aberrations, maybe you should not touch them. They are important. They may allow you to see better. And that's in a moment. That's the most important thing which I wanted to say here, is that sometimes it's worth to look back of what people, particularly good people like Lohmann, he's not with us anymore, but we could learn a lot from him. that's a paper from 1965. Under a certain condition, the transfer function of a defocused lens is demonstrated to be considerably improved by introducing a certain amount of vibration. When I first looked at this paper, and that was more than 10 years ago, it had only a few citations, right? It wasn't a paper that everyone was bragging about. But what my paper, it got me thinking. Maybe in the human eye, we also have a situation like that. Because if you look at people and you measure their aberrations, there is always some amount of defocus, right? Maybe quarter of a diopter, maybe 3/4 of a diopter, and they can still see quite well what is happening. So I decided to do some simulations, okay? And here with Hania Nowicka, who's at the moment finishing her PhD in Cambridge, we did some simulations, okay? And these simulations, we basically look at the visual swell ratio in the optical transfer domain, and we basically added some defocus. Okay, so maybe now I will actually read this here. Okay, so this line here, this is when it starts from a perfect one, okay, because you've got no aberrations in your system. And then as soon as you start adding some vibrations, then we just go like a one sinusoid, no more, okay? Just one sinusoid, and we integrate that information. We basically see how much that image quality would look like if we integrate it all across the whole period, okay? So it goes down. But then when you look at, let's say, a system, that, because we can't call it really an eye here, right? There's nothing about eye here, except that, you know, this conference was about the eye. But the work wasn't. So when you look at the system that it is defocused, just 1/8 of a diopter, then when there is no vibrations, then obviously you've got poor quality. But that quality starts to be high when your vibrations are getting larger. And then the most important thing is actually that area here that is above this curve. Because that area basically tells us that this system performs better than the system in focus. What it means? It means that if I have to live with my dynamics, okay, obviously the best thing is to go back and do everything statically, okay? And when you've got an optical bench, you can do that. But when you've got the eye and it's moving and everything is the heart is pumping blood there, it's a really, really difficult case, right? We can't say, oh, we would prefer to be here at the amplitude of vibration of 0. Yes, but this is impossible. We have some vibrations in the eye. But when we have vibrations in the eye, we can see that this one, it goes quickly down, but if our system is a little bit defocused, it has a chance to be better. So that's basically later on was also done properly mathematically. So we've got 2 papers here. Someone is interested in deriving everything mathematically from scratch using all the integrations. And essentially, if here we just use a model where we have a wavefront and it's got a defocus and spherical aberration, right? It's got the 2 terms. And we allowed defocus to essentially periodically be changed, and also we allowed the spherical aberration, and we end up essentially with the same thing. So those results which I've done with Hania a long time ago, now we confirm that mathematically, because you always like to check what's going on. And what happened recently? Well, recently I have Maciej Bartuzel here, another PhD student of mine, and now student of Professor Szkulmowski in Toruń. So what we decided to do, we decided to perform an experiment. And in this experiment, we basically used a system which is called Murtiao. This is a system which is built at the University of Murcia. It's an adaptive optics system. What essentially, it's got this deformable mirror here, and this deformable mirror allowed us to essentially add the vibrations to the wavefront and see what people would see. And these are, again, simulations. We were not able to perform this kind of simulation because when you've got a real deformable mirror, you can't go sinusoidally. So we actually did a little bit like a trapezoidal wave. But let's focus on what's happening here. This is the same thing which I was telling before. If you are in focus, so you are somewhere here, this through focus curve is taken from one of the subjects, so real aberrations, but simulation with these aberrations. And then when you start doing defocusing here, then you will find out that your integrated image quality drops down. But if you are at 1 diopter of defocus, and then you start with 1 diopter, then your integrating quality is going up. And it's going up because here nothing much is changing, because the difference here is not noticeable. It's bad. But here it's getting better. So someone is happy that they see better. Here, as soon as you add vibrations, the whole thing drops down. So what basically we looked at it in terms of 3D as well. Here you've got the defocus. Here you've got your amplitude of vibration. This blue curve here, which would be equivalent to this blue curve here, is the one without any vibrations. So this is your typical through focus. But then you've got this red one here. The red one, almost like a bifocal here, is when your amplitude of vibration is around 1 diopters. And that green line here, which you see, is the green line when you have a defocused system at 1 diopter and you start to increase your amplitude of vibration. So this is like an overview of what is actually happening with real wavefront data from the human eye. And now the big thing, the results. So what basically happened in that system, we used the Freiburg test. So we are basically looking at the visual acuity. This visual acuity here is expressed in logmar. So here what you have in blue, you have essentially group average results. Well, it's not really average because that's the median and your IQR. These red dots are simply outliers here. And what basically happens is that you've got pretty good vision when your amplitude of vibration is equal to 0, and also when you have everything set up at your focal point. But as soon as you add 1 diopter, so the green here is now 1 diopter defocus, and when you have 1 diopter defocus and no vibration, then obviously your visual acuity is much, much worse. And then as you start adding your vibrations, it gets better and better. And what you see here is what the camera was actually viewing. So that's the case of A, everything is in focus. Here B, we have 1 diopter of defocus. Here we have 1 diopter of defocus and quarter of a diopter of vibrations, and so on until 1 diopter of defocus and 1 diopter of vibration. So basically what we can say is that this is the conclusion, that for the first time, this is to the best of our knowledge and to the knowledge of the reviewers of the paper which just appeared in JOSA, we showed experimentally that both the simulated visual Strel ratio based on the optical transfer function and experimentally measured VA improve when defocus vibrations are added to the defocus eye. So we can basically say now quite with some authority that this case of Lohmann and Paris that was published now quite a long time ago can be related to the dynamics of the human eye, but still there is a lot of questions. We do not know exactly how the visual system copes with all the vibrations in the retinal image quality and whether those changes in the retinal image quality is using it in a destructive or constructive mode. We know that if we have too much of the aberration, then the eye essentially, even though it's ametropic at the beginning, it can start growing and we have myopia, right? So there are certain levels of aberrations that our eye does not know how to cope. But maybe in the majority of cases when we have those dynamics and they are little, and this is the open question which will now conclude this lecture, is does the small defocus that naturally is occurring in the eye contribute to better vision? Thank you very much.
Thank you very much for an interesting talk. And now the talk is open for discussion. Are there any questions? Yes, please.
So you were mentioning correcting with lenses. We can have static lenses, but we can also replace our natural lenses with artificial ones. And if you do this, you get dynamical ones. So they also have, they have pulses. So could this be used to correct the deformation of the cornea?
Well, at this stage, I think it's a far future. I mean, you can imagine that you would have in your eye a device that responds to certain information coming up from, but how would you deal with measuring your aberrations in the first place? Because we can only correct as much as we know that we have to correct. So we need the information about the measurement in the first place, and then have a device that would correct. So having it, like I can't imagine having an adaptive optics system that would be sort of outside and sending information to something like a mirror inside the eye, or a faceplate that would change.
But maybe the natural
very
pulses. I mean, the artificial lens would have some pulses which would come naturally because of the blood.
Okay,
or
so
things like
what you're basically saying, can we take advantage of those movements, micro movements of the intraocular lens, and design it in such a way? Yes, that's possible. Yes,
Thank you.
Quite a neat idea.
As far as I know, I don't know if it's true, it seems that if we put a photosensitive film instead of cornea, the picture will be very much distorted. And it is due to the nervous system that it's improved. So maybe it is so that these vibrations somehow stimulate our nervous system to correct the vision.
Yes, I
What's
agree
your
with that,
opinion
because,
on that?
okay, this is true. The eye has to move for us to see, so that's the first
Yes,
thing.
and it's especially also the small movement of eye. If the eye is immobilized, we stop.
Seeing,
We don't
exactly.
see anymore.
Exactly, that's the case.
So that's.
But the question would be further, like we may sort of think, and some people entertain this idea, whether in the eye we have a system that can be modeled by something which people say it's stochastic resonance. Stochastic resonance happens in nonlinear systems where the noise is not necessarily destructive, but it is taken in a constructive way. You can tune to the noise in order to get better performance of the system. So some people are thinking, I mean, in some animals, in some fish, they use this stochastic resonance approach.
And another thing, it's just interesting for me, I would like to ask you, can you show the power spectrum? In the first part of your talk, you have shown the power spectrum, and there were several peaks. There was a respiration peak, but I would be very much interested. There was a small peak, about 1/10 of hertz. And it's very interesting if this peak is significant. I can't see this picture.
It's
With a power. Oh, this one. Yes. No, this one. Yes. You have this respiration, you have pulse, and there is small peak, about 1/10 of hertz. And this would correspond to so-called Mayer waves. And these Mayer waves, it is a very interesting phenomenon. I have been recently interested in it. And these waves appear in blood pressure, in heart rate variability, also in the levels of the oxygenation and deoxygenation in the blood, and also in EEG, as a modulations of rhythms.
Okay, this is very
And
interesting.
it's very, this phenomenon I think is very interesting, but maybe it has something to do with the overall regulation of our organism. We have been looking at by means of multivariate autoregressive model, at these waves in different signals, and in fact they are very much connected by there are reciprocal connections between them. And there are two theories. Either they are they are due mainly to the baroreflex, or they are generated in brainstem or some.
Okay.
And
I'm
it
not
will be
familiar-
very interesting to know if they also appear in your signals.
Sure.
Is this peak significant or not?
Okay, so just to tell you, I don't take that particular peak into account much because I only measured this signal for 20 seconds. So my frequency resolution at those low frequencies, I don't trust them much. But this is a very interesting suggestion, and I would like
But
to talk to
maybe
you
it would
later.
be- it would be worth
Because
to
maybe
look
if
at
we
it,
measured
yes.
that signal for, let's say, a minute or two, then we could have.
Yes,
this is
because
just a
they are very
periodogram, by the
slow,
way,
so you have to-
So it's a poor estimator of the spectral information.
Okay, thank you.
Okay.
How do you assess the level of repeatability of the measurements?
Okay, this is, well, almost like a classical question. Well, first of all, when I'm assuming that you are interested in wavefront aberrations, right? When we deal with wavefront aberrations, we use two approaches. One approach is that the person is actually not changing the way it sits in front of the instrument. Essentially, the person actually is connected to the instrument with a bite bar, and sometimes we also use a head strap. And then we do repeated measurements. We take several, right? Sometimes it's 3, sometimes it's 10, sometimes it's 20. How we decide whether 3 is enough or 20 or is enough? Well, we basically look at the cumulative variance and try to find out where we should stop when this information is reliable. But we also deal with a lot of clinical subjects. And when we talk about clinical subjects, you can't put them in a bite bar. You know, volunteers and students are happy to do that, but not necessarily a 90-year-old woman, for example, right, who is fragile and is not able to be restrained in such a way. So what we basically do, we take a measurement and then we allow the subject to sit back, relax, and then we take another measurement and another measurement. And what you've seen in those 4 measurements, which I was showing you a little sort of simulation of the wavefront, that was the case where the subject was coming to the headrest, we've done the measurement, and then it was sitting back, and then another measurement. And so these were not sort of a set of continuous measurements. But we wanted to actually see how that performs in real life. And obviously, we use statistical tools and statistical analysis to find out whether our measurements are, repeatability is one thing, but I would say we cannot really test repeatability. We normally test reproducibility, because repeatability means that we are not changing the conditions of our measurement, right? But from, like, if someone sat and then comes back to the instrument, this is called reproducibility of our measurements.
Are there any more questions? If not, let's thank the speaker one more time.
Thank you very much. My pleasure.